So our next speaker probably has more experience with lunar dust than most of the rest of us. We will be hearing from Jack Schmitt on dust and the layered defense. And so we'll work on getting those slides up here in just a second, and then Jack can take it away.
Okay, well, it's great to be with everybody. Enjoyed the presentations up to now. Obviously, if we were in the same room, I'd have lots of questions about some of the assumptions that have been made, but let's press on. If I could have the next slide, please. We were asked to look at the top dust impacts on Artemis exploration, and I would give you these two. The EMU, all included, is the primary vector for dust into the lunar cabin. The first solution, which I've advocated for 50 years, is to have EMU surfaces, and I would add to that the sample bag surfaces, by the way, reject dust automatically. If you don't take dust into the cabin, you have much less of a problem. An alternative, not quite so good because it takes time and mass, but is a disposable cover for the suit and the PLIS, one per astronaut and one per EVA. I seriously consider a non-solution is Apollo-style brushing, and some of the briefings that I've had on the XEMU suggest that that's what NASA is depending on at this point in time. It's time-consuming and energy-consuming and does not do much of a job. In fact, I don't think it gets rid of anything significant. And the second impact is the disabling of moving parts on various tools. And the solution there is far beyond me, but it's good engineering. You just can't have connectors that for tools that are going to be exposed to dust. By our end of our second EVA, the extension handle connection to the various tools was inoperable. And the adjustment on the scoop was also inoperable. So somebody needs to come up with a great idea about how to keep dust out of those connectors. Now, a possible solution, replacement parts, but there's a mass penalty for doing that. And you might take the connectors into the cabin and clean them between each EVA. Neither one of those are very ideal, but there are possible interim solutions until we come up with good engineering. Next. An in-cabin defense against rogue dust. Some dust almost certainly will get into the cabin. The idea of a layered defense is to keep most of that out. But as far as inhalations are concerned, if you have a good filtering system, just don't take the helmets off until the cabin air is largely filtered. I have suggested on other occasions, after Larry Taylor and I had discussed this for many years, is the use of electromagnetic filters with an off function for cleaning, either moist cloth or sticky tape or some other system can be worked out. A disposable dust trapping fabric on the floor surface, but you have to remember that ascent cutoff, dust on the floor and everywhere else will need to be filtered out of the cabin. That may be the point where the filtering system gets its highest impact in terms of mass of dust. Next, please. Now, just some reminders. Many of these have been addressed already today, but I'll just go through them again. About 50% of the dust is less than 100 microns, and about 1% is less than 1 micron. And that is probably the dust that we need to be most concerned about from a physiological point of view. More on that in a moment. The agglutinate particles, which are up to 50% in some samples, have jagged fractal surfaces. The specific gravity of the particles varies, and this between 2.6 for glass and 4.2 for ilmenite, and actually that 2.6 is probably high. Pardon the puff in the background there. and it's high because these agglutinated glasses are vesicular. They have holes in them that will reduce that specific gravity. But remember that it's the specific gravity of particles we have to deal with in the cabin is not the specific gravity of the regolith itself. They are the specific gravity of the individual particles. Now, each particle is magnetic. There's nanophase iron in coatings on almost every particle. Each particle has unsatisfied electron bonds, which out in the lunar environment makes it slightly cohesive. But in the cabin, and once it absorbs cabin air, that cohesiveness will disappear. Disturbed in situ lunar dust does not billow. Every once in a while you hear somebody talk in terms of that suggests they have assumed that it's billowing during landing. It's not. They're ballistic trajectories. Everything moves away from the force that has accelerated it. The 5 to 10% of individuals have some allergic reaction from mild to severe. Now, we don't have a large N on that estimate. I had a little bit of a hay fever symptom when I inhaled the dust, and that gradually went away over 3 excursions. But there was one flight surgeon who was assigned to remove the suits from the command module after it was splashdown, who had such a reaction that he could not continue, and he needed to be replaced to do that job. So there are issues here that are individual, and so you don't want to have a chronic exposure to this dust. On the other hand, there's no evidence of permanent physiological damage with astronauts, and we've had really at least 4 times 6 inhalations on 6 crewmen. The J mission, Apollo 15, 16, and 17, had the most inhalations, and to my knowledge, there's never been any evidence that those inhalations have caused any physiological problem. Initially, high surface bearing strength outside decreases with traffic. All you have to do is look at the photographs to see how the surface of the dust fluffs up, and long-term stabilization of those surfaces is going to have to be dealt with. And finally, the adhered and embedded solar wind particles, hydrogen, helium, carbon, and nitrogen can be present and probably are present in most regolith at 100 to 200 parts per million, which means that about close to 1% of the regolith will have solar wind volatiles either adhering or embedded in it. Now, at the north and south poles, there is a question about what else might be there, and so some ice particles might be in that dust. We'll just have to wait and see once we get there and have a chance to sample it. And the next slide, just to remind you that scientifically there's some good dust. The average particle size of the pyroclastic ash that we discovered at Shorty Crater was less than 40 microns. Most of that ash actually turns out to have been shards of beads of glass, and those shards would be, of course, much more of concern if we run into some extensive areas of pyroclastic ash. And with that, I'd be happy to take any questions that we have time for.
Great, thanks, Jack. Yeah, we have time for a quick question from Jeff Gillis-Davis. He asks, is the lack of permanent damage, I think he's referring to the physiological damage, related to the short duration of exposure, and what can we expect for longer term exposures of weeks to months?
Well, I think, clearly our experience here on Earth with silicosis and other things says that you don't want to have long-term exposure to any kind of mineral dust. And so we need to make sure that those inhalations don't occur over a long period of time. I'm just saying that with the 4 inhalations that I had and many of my colleagues had, there's no evidence of any physiological damage that I'm aware of. Now, that's something for the physiologist to confirm. Unfortunately, we did not have in our longitudinal studies the right protocols in order to really analyze that issue.
Great. Thanks, Jack.